And thanks for inviting me. I wish I could be in Amsterdam. I love Amsterdam. It would be great to visit maybe sometime in the future. But yeah, today I'm in Oakland, California, which is in the Bay Area, right across the bridge from San Francisco. And I should also mention I have my dog with me right now. Like, he sometimes is gone when I try to do presentations, but today he's not, and he might bark. He's got a lot of anxiety, so if he hears a truck or something on the street, I'll try to mute myself if that happens, but yeah, we'll see how it goes. Okay, so yeah, I'm gonna talk about some new stuff that we released in my team into H2O. I think it was in October, so it's pretty new, and this is the first meetup that I've talked about it. So so I actually had to make new slides, which was usually I like reusing a lot of my content, but this is all, well, not all new content. This is half new content today. So I've given a lot of talk so far about H2O AutoML, but now we have the ability to kind of explain the models, or to like look inside them and just get a more deeper understanding of what we're doing with AutoML. So I will just briefly just talk about what is H2O. In the R world, it's just a library called H2O that you can get from CRAN. And we have a Python API and Java and Scala. So I'm only going to be talking about the R today, but just as a note. So this is sort of just an overview of what it is. It's a package that if you're doing any kind of, or if you have done any kind of machine learning in R, the closest thing that it would be like is something like the Carrot package, and now we have like the Tidy Models package. So what that means is like it's a package that has a whole bunch of algorithms in it with a common interface. And the big difference is that those other packages are more of like a layer on top of a lot of other machine learning packages, whereas H2O is just, we have written all the algorithms from scratch. So it's not really like a interface to other things. It just is, I guess, having a bunch of algorithms on its own. And one of the reasons that we made this package to begin with is because basically to be able to scale to large data sets. So when this whole H2O effort started, it was back in 2012, and that was 8 years ago now. And at that time, if you were working in data science or machine learning, like the thing that everybody was focused on was what they call big data, which I think is kind of just a weird term, but everybody was talking about big data at that time. And so one of the things that people were seeing is like, you're trying to do all this machine learning and it's like running not fast enough, or it doesn't scale enough, or you don't have enough memory to run it on these large data sets. So one of the reasons that we created H2O was, and I actually wasn't at the company when it started, so I'm saying we, but this thinking was predated my involvement. But basically the goal was to have very, very fast, very, very scalable machine learning algorithms available for data scientists to use. And that's one of the ways that we did that was we implemented them in Java, which is, you know, you could use something like C++ or Java, something fast, and then we make interfaces to R and Python, which are the two main languages that data scientists would like to use. And then another goal, I guess, was to make something that you could deploy into production. So what was happening back then, and still happens a lot now, is that people sort of prototype in R and Python, and then maybe if they are running some kind of, if you're at like a company like, like eBay or Amazon or something where you're needing to like produce predictions really, really, really fast at like a large scale, you have to use like more high performance code. So the idea was to be able to still write the code in R and Python and then be able to productionize in Java without having to rewrite everything in Java or C++. So that's kind of the whole philosophy of why H2O exists. And it also works like with Hadoop or Spark or some of these other big data platforms. But most of the time, people just use it as a normal library on their laptop. So that's what I'm going to be talking about, like, and that's how probably most people use it. And it's very straightforward. You don't have to know anything about big data or high performance computing or anything like that. It's just an R library essentially to the R user. And then inside of H2O, we have a whole bunch of different algorithms, both supervised and unsupervised. So some just examples: gradient boosting machines, random forests, deep neural networks, GLM, stacked ensembles. We also have XGBoost, which is one of, I think it's the only like third-party library that we bundle in with H2O. It's just another GBM library that's very good. And then another thing that we try to do is try to automate a lot of like the steps that are always required in machine learning. So if you have like missing data or you need to like encode your categoricals in some way, we just try to do that sort of automatically. In other like libraries, usually you have to write code explicitly to do all those steps. So we try to just make it as easy as possible by doing some of that stuff automatically. And another thing that we, you know, and maybe you're starting to get a theme, is like we try to automate things that are can be automated in a pretty straightforward way. So things like how to tune the models. We have something called automatic early stopping. So like, for example, when you're training a GBM or like a gradient boosting machine, what you're doing is like you keep doing iterations of the training. So you add more trees or things like that. Deep learning has the same concept. So what's easy to do is like you can actually train too much, and then when you bring it over to the test set, it's like not doing so well. So what we do is a way of like just figuring out to like stop the training at the appropriate time automatically, so that you don't have to like manually like plot it out and plot the validation error and the training error and like look and see exactly where it's, you know, if you're not super familiar with like tuning machine learning models, this probably doesn't make a lot of sense. But anyway, it's just a way to get better performance essentially with less work. And then we have other stuff that's sort of related to machine learning, or sort of the infrastructure for machine learning. So things like cross-validation and grid search and random search. And then once you have the models, we have everything that you need, like variable importance, any kind of like model performance metrics like mean squared error, accuracy, AUC, etc. There's some plots, and now we have model explainability stuff as well, which I'll talk about. So it's meant to be kind of like a full-featured library. And you should be able to sort of do everything with H2O without bringing in a whole bunch of other different libraries. Okay, so now I'm going to talk about AutoML. So I mentioned we have a whole bunch of different algorithms in H2O. So one of the things that I found myself doing while I was developing H2O and also using H2O was I would find myself like doing a lot of the same thing over and over. So I would train a whole bunch of models, and then I would stack them together with stacked ensembles, and then I would like, that was kind of my process. So essentially what I did was write a wrapper function for this whole thing that I do that's like my data science process, and then we call that AutoML. And I'll get into a little bit more detail about that. But so now, like AutoML is a thing that's been around for a while, but it's really only getting a lot of popularity in the last couple of years because there weren't really a lot of libraries that would do this easily. And there was some like sort of, let's say like you could call them an AutoML library, where it would just sort of try to automatically tune a single algorithm, which is like one thing. But really our goal is to we don't want to have to think about which algorithm to use, because every data set is different. You never know sort of in advance what's going to be the right model and what are going to be the right hyperparameter values for that data set. So we want to have sort of a more broad solution where we can look at any kind of different algorithm and all the different combinations of these different algorithms. But AutoML in general is really about just making things a little bit more simple and getting better results. So I think, like, if I had to summarize what the point of AutoML is, it's really just to get the best model that you can with like the least amount of effort. And that effort can be, it can be in terms of writing code, like how much code do you have to write to get that model? And then it's also can be in terms of like how much computation power or time do you need to spend to get that model? So we want to like really reduce both of those time frames to make it more efficient. And then what it also does is, because it's sort of just this abstraction, or it's sort of just this generic supervised machine learning algorithm where it doesn't really even, I mean, there are parameters that you can set, but essentially you're just stripping everything away to the point where you just say, here's my data set, here's the thing I'm trying to predict, and then like, here's how much time I want you to spend doing it, essentially. And then possibly you could say, I'm going to measure the model based on log loss or AUC, so I want you to focus on maximizing AUC or log loss. But we have some defaults built in. But usually I would say, like, data science or machine learning people have some idea of like, I want to maximize AUC if it's a binary classification problem or something like that. So you can tweak all of this stuff. The H2O AutoML function does have quite a large number of parameters that you can customize, but we try to have everything sort of set to good defaults and have it be automatic. So this is sort of a feature of AutoML, that it makes it easier for people who don't know that much about every single machine learning algorithm and how they work to train good models. You just have to have the general framework of machine learning understood in your mind, and then you can use it. And so I think a lot of people I see are either like really into tree-based models, or they're like maybe really into deep learning, or maybe they're really into have a favorite algorithm. At least I've noticed that. Maybe that's changing over the years, but when you kind of have something, I mean, people usually choose that algorithm because they spend a lot of time using it and they get really good at tuning that type of thing. So I think people tend to overlook other algorithms sometimes when they're experimenting, because they just want to use the one that they know about and that they're good at using. So I think that's, you kind of overlook good solutions that might be there sometimes. So I think that's not really on my slides here, but and then in general, like, the goal would be to, get better models than like, let's say the average data scientist could get. I would say right now, the state of AutoML is like, if you're a very expert machine learning person, you can probably beat all the AutoML tools that are out there if you really put your mind to it. And especially if you focus on feature engineering, because that's one area where the AutoML tools that are out there don't focus on as much. And yeah, another good use case for it is like, if you're writing a paper, let's say you're not really even a machine learning person, but you're some kind of other scientist, and you want to use machine learning because you think it's this cool thing, and you see a use for it in your work. I would totally recommend using an AutoML tool, because in that case, that you're probably going to get pretty good models without like having to mess around too much. And what I see a lot in science and people trying to use machine learning for the first time is that they'll write a big paper, and then they train like a random forest, and like with all the default parameters, and they're like, here, I did this machine learning. And it's like, okay, well, we know, I guess machine learning can work like a little bit, but we're not sure what the real potential is because you didn't really try all this other stuff. We don't really know. We know like it can do at least that well. And that's just because like if you're not like, if your day job is not doing machine learning and training models and all this stuff, like, you know, it's a big achievement if you can even just use a random forest library in itself. So I think I would love to see more people just, you know, dropping in an AutoML tool rather than something like a random forest or GLM. Okay, so I better keep talking because I am going on and on. So, so the types of tasks that we want to automate in machine learning are, I think, can be kind of divided into a few categories. So we have like the data, anything to do with the data and preparing the data or encoding the variables in certain ways and creating new variables or variable selection or any of that stuff could be in kind of the data prep category. Then we have like this part where we need to just generate a bunch of models, because at this point, you can't necessarily predict what the right model is going to be without doing a whole bunch of work. And I do think that actually the AutoML field is going to get to the point where we can predict and we don't actually have to do all the computing to get there. That's kind of a trend in a research area in AutoML, so that might be changing over time. But for now, if you want to be sure that you're going to get a good model, you really just have to compute a bunch of models and find the best one. And then something that I personally like to do, but maybe not everybody does, is once you have a bunch of models, you can ensemble them together to get a better model. And then I'm just going to quickly point you to this blog post if you're interested in learning about like the different types of AutoML, because now there's a whole bunch of companies that do AutoML, and all of the big sort of tech companies like Google or Microsoft or Amazon, they're all having their own AutoML now. But a lot of them are actually related to image classification or text or other things. So I'm in this article, I just try to break down like the different types of AutoML. And what we're going to talk about today is like AutoML for tabular data. So not image classification, not text, just like normal, you know, tabular data, like an Excel spreadsheet. Okay, so here's those three categories that I listed before, but I'm just kind of highlighting some of the things that we do. So this is kind of a list of like all, you know, maybe some more things that could fall into these categories, but in our particular case, how I've written the algorithm is that we're doing these specific things. So we do some basic data pre-processing to kind of deal with missing data or encoding or whatnot. And then one of the options, and this is actually not turned on by default at this point, is something called target encoding. So that can be very helpful if you have columns in your data set where there's a lot of categories. Like let's say, you know, you have 5,000 different levels in your, you know, column. And that type of data creates a lot of problems for machine learning software and algorithms. So there's sometimes the need to, you know, transform that type of column into something else before you actually hand it over to a machine learning algorithm. One of those ways is called target encoding. I'm not going to explain what that is, but it's something that we do. And then in terms of like model generation, the kind of the two main ways, there's probably like, you know, many ways. I could probably think of like at least 6 different ways of tuning models off the top of my head, but kind of the two main paradigms are something like more, what's the word? I'm blanking on the word, but basically like the brute force approach is that's the term I'm looking for. So there's something like grid search or random search. So you kind of just like throw a bunch of things, you know, out there and see what happens. And that's something, it's sort of the least sophisticated technique, but it's also the easiest to do in parallel, and because you could just do it all at once, basically. So that's kind of a nice feature. And then there's something called Bayesian hyperparameter optimization, which we don't currently do. And that's more of like a sequential, step-by-step, like getting better each time type of approach. And that is also a very good approach. The only drawback is that you can't really parallelize that. You have to do it one after the other. So if you have more computation power, you can get to a better solution quicker if you do random search, you know, if you just throw a bunch of computation power at it. So, and then in terms of ensembles, the type of ensembling that I like to do the most is called stacking or super learning or stacked ensembles, but there are other types of ensembles techniques out there. And so this is basically what we do in AutoML. We're doing like a random grid search. It's not random in the sense that we don't have any constraints on it, but we've sort of identified which hyperparameters are worth tuning and what the ranges should be. And then within that, then we randomize things and generate models that way. And then once we've done that with sort of all the algorithms, like we do that with GBM, deep learning, et cetera, then we create a stacked ensemble using those models. And one of the reasons that those two things work well together is because stacked ensembles work really well if the base learners or the models in the ensemble are sort of diverse and like basically failing in different ways. So if one model, you know, does poorly on a certain data point, then maybe the other one will do well, is kind of the idea. And so this is just another lesson, life lesson, really, that diversity is important and useful, I think. So, so there's sort of mathematical backing behind it. And so, yeah, this is just a summary of what I've said. So, I mean, I'm just sort of explaining to you, we're going to spend more time on the other part of the talk, but, you know, there's lots of different ways to do AutoML, but basically, you know, you just pick some technique of getting a good model, and then hopefully, you know, it works. And I would say all the AutoML tools out there are doing something different. And most of the AutoML tools out there are in Python right now. So in R, there's H2O AutoML, and there's two others that are in development by like people that I know. And one of them is on top of the MLR library, which is another library like Carrot or Tidy Models. You might be familiar. It's created in Europe, so it might be more popular in Europe versus the US. I don't know. But that's, and I know the people that work on that, and it's a very good library. So there's one that's being built on top of that. But for the most part, there's not that many libraries yet, and most of them are in Python, and most of them are compatible with scikit-learn. Yeah, so when you're done with the AutoML training, what you get back is something that we call a leaderboard, and I'll show you what that is in a minute. Let me just show you what the R code looks like. So this is how you do the whole thing. So you load the library. With H2O, we have this function that you always have to execute at the beginning of a script, which is called h2o.init. And what that does is it starts up the H2O cluster. And I'm not going to go into a whole lot of detail about that, but essentially what that means is it's starting a Java process on your machine where all of the machine learning and all of that stuff is happening, because the actual training and all of the computation is all in Java. And so R is just sort of an interface to that. So you start up what we call the H2O cluster, and that's where all the data lives as well. So when you do this h2o.import file, it loads like a CSV file into the cluster. And so it's none of the data or the models is actually in memory in R. They're all just like pointers to it. You can also take like a normal R data frame or a tibble and convert it into what we call an H2O frame. So that train object is not like, if you looked at what it is in R, if you did class train, it would say H2O frame. So it's not a data.frame, it's not a tibble, it's not a data table, it's its own thing, but it works like a data frame. And you can subset the rows and do all the stuff like the same as like a data frame. But it's sort of its own structure. And that's when I talk about H2O, it's more of like a platform rather than a machine learning library, because it kind of gives you all this infrastructure, including these like distributed data frames that can be scaled onto like very large clusters. So that's not important. You just treat it like a data frame in your mind. And so to do the training, then we do H2O.AutoML. And then, like I said, this is like the bare bones, like what you would have to give it. There's other arguments that you can set, but all you really need is like, what's your training data? What's the column that you're trying to predict? And how long do you want to run for? And then you go. So this is like, run this for 10 minutes, basically. And then once it's done, then you have this object, AML, I've called it, and then there's different things that were stored in there. So one of the main things that you want to look at is what we call the leaderboard, because that's going to show you what models got trained and like what their performance is comparing to each other. So this is what it might look like. So it's basically just a data frame with some information. And in the first column, you'll have the name of the models. So these are just IDs. You can't really understand a whole lot about it other than what type of algorithm was used. So which is helpful, and it's kind of interesting to see that, but you'll have to actually look at the model and see what all the parameters are to get more insight. But for now, you can see, like in this case, we trained an AutoML run, and the winner here was a stacked ensemble model. So we trained actually 2 different stacked ensembles. One is with all the models, and we just call that stacked ensemble all models. And that usually is the best model. But because, depending on how many models you train, it could be like 100 models, it could be 1,000 models, it could be like 10,000 models, whatever. I mean, it's usually not, probably people aren't using it like that, but it could be quite a large ensemble. So that might not be so efficient for if you want to put these into production. So, because anytime you make a prediction from a stacked ensemble, it first has to ask all of its ensemble members, so all the models that are inside, to make their predictions, and then that gets fed into another function, and then that becomes the final prediction. So it is like possible to do all of that in parallel, but it's just a lot of overhead if you don't really need it. So then we have something that's called the best of family, which just basically makes an ensemble from like the best GBM, the best XGBoost, the best random forest, the best GLM, and the best deep neural net. And so it's, I don't know, I think there's like, I forget the count, six models in there. So it's a more lightweight one. If you still want to get the better performance, but you have it be like more efficient and faster at making predictions. Yeah, so in this case, we just see this is a binary classification problem. So by default, we're ranking them by a 5-fold cross-validated AUC. And then you have all the other metrics there. I think there are more metrics, but they did not fit on my page, so I cut them off. Yeah, so that's basically what you get. And you don't have to choose the one that does the best, or you can resort them. We have what we call an extended leaderboard, so you can actually generate additional columns that are providing you like training time, or probably the most useful one is the prediction speed. So if you're trying to deploy something into production, you want to know how fast it is at making predictions, because maybe your top model is best in terms of accuracy, but maybe it's much slower. So if you just went like a little bit less in terms of the accuracy, you could get a much faster model. So it's good to have like the extra context when you're choosing which model to use, because you don't have to use the one that's the leader model. We just call the one that's sort of at the top, ranked by performance, the leader model. So you have a lot of different ways that you can choose a model. And one of the other things that I'm going to go into, I'm going to talk about explainability, is like maybe there's other things that you want to consider, like maybe the models are more explainable, or maybe there's other features that we can observe by looking at some of these explanations of the model that would lead us to choosing a different model. I think I'll skip over this. I just kind of put this in the slide so you can have it. I just like to send people with some pro tips, like how to use AutoML well. I think I will skip over this. This is just talking a little bit about how to configure it and how you can turn on and off certain algorithms if you want. You can change the cross-validation strategy to make it faster if you don't want to spend so much time on cross-validation. You can also control how long AutoML runs by saying how many models you want it to produce rather than the time, or you can use them both together. And then this is something also maybe a little out of scope, but just something that if you are going to train, let's say 100 or 1,000 models, you need to have enough memory to store all the models. So if that is the case that you're having memory issues, then you can adjust the size of the memory used in the h2o.init command. So because we're trying to build a tool that works for big data, we're very careful and precise about how we use memory. So this is not something that normally in R you have to think about, or that you kind of have whatever the memory is on your computer, and if it fits, it fits, and if not, like whatever, so here we can actually like control the memory and make it bigger and smaller if we want. Okay. So the next thing, okay, so now we're going to talk about explainability. And so this is also developed by my team, and we have this new function that's called h2o.explain. And what you can do is you can pass along a single model, or you can give it like a list of models or a group of models. So if you can actually give it an AutoML object itself. So it can be used in both ways. And if you give it a group of models, basically what it will do is it will give you some extra plots that do sort of multi-model comparisons that you won't get if you give it just a single model. And something to note about like model explainability. So there's kind of two levels of explaining models. One is like you're explaining the whole model itself. And then the other is like you're trying to explain like a single prediction. So like you make a prediction using one row, and you want to kind of understand how did it come to predicting that it was 0.6 or whatever the output is. So that would be when I was like younger and doing like other things, I was doing consulting and in machine learning, and I train a model and I would make all these predictions, and then the people would be like, why are you scoring this particular thing so high? I don't understand. And I was like, I don't know. I mean, I know it's a good model that I'm using, so I believe like what it's saying, but there was at that time, this is like in like 2011 or something like that, there weren't tools to like help explain why it was. And so in that particular case, what I was doing is trying to predict whether or not Android apps were malware or not, and assigning some kind of like score to that. So they would give it a new app, and it would score like a we mapped it to like a 0 to 10 scale, so it would give it like a 9, and they'd be like, why does this thing get a 9? It's just like a banking app, and like this doesn't make any sense, and I don't believe your magical machine learning. I don't like it, and I don't believe it. And so it was very frustrating because I couldn't really explain why. And I knew that the model that I had trained was a very strong model with like an AUC of 0.98. So I was like pretty confident this model was doing a good job. And really what that meant in this context was that it was probably actually malware, and they just didn't realize it. But it's really hard to convince people, and especially 10 years ago when people were very like anti-machine learning. Now it's probably like way too much the other way, where they're like, oh, well, the model said so like that's fine, and they don't question it. So now we're trying to like get people to still question these things, but like in a smart way that makes sense, that everybody can understand. So So some of the new stuff that we've added is all sorts of like different variable importance comparisons. I'll show you examples of all this. And we look at different like the correlation between models. So that can be interesting. Like if you're trying to make a decision between model A and model B, and like if they're like maybe they're kind of like highly correlated, and like one of them has good properties and one of them doesn't, you might want to pick like the one that has the good properties. So it's, I don't know, there's lots of different uses for that. I won't go into more detail, but then there's something that's called SHAP or Shapley. SHAP, basically this has to do with like explaining predictions. The way that it's used most often, I think, is when you're trying to explain like a single row, like why is this prediction 0.6? Like what were the features that contributed and how much did they contribute, and can I really get a sense of that? And then like kind of look for things that don't seem right. I mean, basically that's what these tools are, is they're like little like investigator tools where you can kind of see if something's going wrong or it doesn't make sense. Like if you have some domain expertise about the data and you see the model doing something very weird, like these are very useful tools to detect that. Because sometimes models are just bad and you shouldn't use them, and there's all sorts of reasons. And even if their AUC is good. Then there's something called partial dependence plots and individual conditional expectation plots. I'll talk about that as well. And then something called residual analysis. That's just for regression. You might have heard of that if you're a statistician. And that's a link on the bottom there to the documentation. So yeah, in my slides, I have a bunch of I have all the plots that we produce. And it actually, I don't know, it might be easier to show you all of the plots on the actual web documentation site, because they have all the explanations. So why don't we start here and maybe we'll switch over to that, I'll see. So yeah, so for residual analysis, it's basically looking at like, what is the difference between the predicted value like and the actual value, and kind of looking at any patterns there. This is kind of a weird one because in this data set that I'm using on this, I'm like pointing to my screen, but you can't see me pointing, but that the URL at the bottom, the explainability user guide, we use an example where you're predicting wine quality. So there's some data set where people have scored like how, I don't know, good wine is or something. And it's on, I think it's on a scale from like 1 to 10. And so it is a regression problem, but the values are discrete. So, it's 0, 1, 2, 3, 4, 5. It can't be, I guess people weren't allowed to say this is a 4.5 wine or any number in between. So that's why you see this kind of striping pattern. If anybody's familiar with residual analysis, this will make sense. But residual analysis plots usually look a little bit different if the data is actually continuous and not discrete. So this is just variable importance. So this is something that probably most people are familiar with already, because this is quite common and not necessarily considered like an explainability method per se. But so this would look at, like for this particular XGBoost model, we're looking at all the different variables here. So I'll just read some of them in case you can't see that. So the top one is alcohol content. So what's kind of interesting is like, people seem to just like wine if it has more alcohol in it. It's like basically the story. There's other things apparently, but that's a very strong indicator, which is kind of funny. So then there's like acidity, how much sulfur oxide is in the wine, different like chemical attributes of the wine. So the idea is like maybe there's some like intrinsic goodness in the wine that can be measured in a chemical way. Sugar, pH, sulfate. Yeah, so that's basically what they were looking for. It probably would have been like I mean, if you were to redo this data set and like put like marketing materials around wine or the price or other things, that would probably skew people's view of what the wine is. I'm assuming this was like a blind study where we only could taste the wine and couldn't see the bottle or things like that. But I think that would be interesting to look at. Okay, so then this is an example of if we pass along an AutoML run to the explain function, it will create this heat map. So it will actually take all the model, well, not all the models. It'll basically take the top 20 models, and you can adjust the number, but by default, like we just chose, I think it was 20. And it will just compare the variable importance scores for each of the models. So that can be kind of interesting to look at as well. So I have the zoom thing, I think hiding the right-hand side of this plot, so I can't tell if there's actually the scale on there. But yeah, I mean, maybe something to look at. I mean, you would kind of hope that all the models would perceive the importance of the variables in the same way, but there are differences in between algorithms that you know, sort of you interpret the data in different ways, and you can kind of get different variable importances. So something to remember, like when you're looking at variable importance, is like that's very contextualized to like the particular algorithm that you've used. So probably all the, you know, the GBMs might look kind of similar to each other, but they might look very different than like how the GLM thinks the variables are important. And it's just kind of an interesting thing to look at. Okay. I guess one thing I'll note is like the one on the bottom left, it says there's this model GBM grid 1, model 3. That's seeming to like weigh alcohol way higher than all the other models for some reason. So that's kind of interesting. And then this is like how all the models are correlated together. So again, this might not be so useful for debugging, like to decide if a model is good to use or not, but it might be a tool that you could use to choose between models. So like, let's say you had, you know, a model that was, you know, good, but maybe it's like a very slow predicting model. So maybe you want to find one that's correlated to it that that has other attributes that you like, or something like that. It's also, when you're using stacked ensembles, kind of interesting to observe how much diversity is in there, to see if there is kind of enough diversity, or maybe you need to generate more models to get that. So this is a SHAP summary plot. So, I mentioned before, one of the main use cases of SHAP is to sort of understand on a row-wise prediction level how the how much each of the variables are contributing to that single prediction. So that's sort of maybe the default use case, but then you could do that like by doing you could evaluate that for all the examples in your data set, and then kind of generate this this other kind of plot that kind of shows you, it's almost like it's just a normal variable importance plot, but it's generated in like a different way on a row-wise basis and then aggregated. And I won't sort of go into a lot of details. Maybe we'll visit the user guide page after, and we can answer questions. So this is like the row-wise explanation. So when somebody says like, why does this particular wine like score, you know, here you can see on the plot, it actually says like the score was 6, so 6 out of 10. So why did this one score 6? You can say, okay, well, it was because there was a lot of like, or not a lot of, but like there was, let's see. Oh, sorry. And on the left-hand side, it actually has the values for each of the features. So in this particular wine, the free sulfur oxide was 30, and the total sulfur oxide was 97. The pH was 3.26. So you can actually see exactly like what the feature values are, and then how they're being like weighted. And that free sulfur oxide being 30 was like highly leading to the prediction being 6. I don't know if I'm doing a great job explaining everything because I'm trying to like rush through lots of different plots, but that's why I'll point you to the user guide where you can actually read more about the plots. And then this one I think is nice. So partial dependence I think is quite straightforward to understand. So maybe I'll try to explain that. So actually before, I'll skip ahead because this is the partial dependence for a single model. So basically what you see here is that middle line is the average among all the data points. And what you see, so you can kind of treat that as like the thing your eyes should follow. And then those are kind of just confidence, or not confidence bands, but like bands of all the other data around it. So what you're seeing here is like basically as the alcohol content increases, so on the x-axis we have alcohol content, and then on the y-axis we have the response. Basically there's a correlation between, and the response is the score of the alcohol, right? That's the thing that we're trying to predict. So basically as alcohol content increases, the score of the wine increases. That's basically what you're seeing here. So we also saw evidence for that in the variable importance plot to begin with. So yeah, there's basically like a trend, like put more alcohol in the wine, people like it better. And then I'll go back to this one where we actually, we have the partial dependence plots for all, or not all the models, but basically the best deep learning model, best random forest. DRF is the random forest, that it stands for distributed random forest. XRT is another one that you probably wouldn't recognize, but it stands for extremely randomized trees, which is another version of random forest. So these are just kind of like the best models from each category, and then we can kind of see how they're different. And but what you do see is there's still like all the models are still able to capture the trend that like the more alcohol, the higher the score. There's one, which one is it? It's, there's the brown one that's XGBoost, which seems to have a slightly different ending point. So maybe at a certain point in this model, it's thinking that if you put in too much alcohol, it actually like lowers the score a little bit, but okay. All right, so then this is basically the same thing as what you see before, except for it's for a single row. So I'm going to kind of skip over these parts, and then I wanted to just bring you to the user guide real quick so that you can find, I promised there would be code. So I'm gonna stop sharing my slides and I'm gonna open up a browser real quick to show you the user guide. And I'm gonna share that instead. Okay, so what you're seeing now is, excuse me, is the documentation site. So yeah, if you go to, well, that's what the first tab is docs.h2o.ai. That's like our main documentation page. We have many different tools at this point, but this is called H2O3. The 3 is just kind of, it's the third version of H2O that we've written, and that's where the 3 comes from. It's also the name of the GitHub repo. It's like H2O-3. But you can just call it H2O. So if we click on the user guide, that'll bring us here. And I'm in the AutoML section, but you know, this is where you can learn doing. There's some information about like how to install H2O. I mean, it's a little bit overly like informative, like basically just go in RStudio, type in H2O and you know, install from CRAN. The one, the one thing that you do need to run H2O is that you need Java to be installed on your machine. So that's probably the one thing that sometimes can be hard for people. Almost like most people don't have problems installing Java, but that is like the pain point that we see for people that, I don't know, like things can just get weird on people's machines. And like, if you have a work machine, like things, sometimes it's hard to install stuff. So, I mean, the way that you can check if you have Java is you can open up a console, like a shell, like command line, and type in Java -- version and hit enter. And if it says some version, then you have Java. So, and probably the version that you have is okay. There are some versions of Java that are not supported, but probably, you know, unless you've either have a very, very old version, or if Java has just released a new version and you downloaded it and we don't officially support it yet, then you could also need to get a different version. But so yeah, that's basically what you do. So as long as you have Java, there are 2 other dependencies, but if you just install from CRAN, it should install those for you. So, but anyway, if you have problems, you can let me know, because I've solved installing H2O many times and can probably fix your problem. So yeah, the places that I would look, like, this is like useful for, you know, if you need to know how to do data manipulation, like, you know, all this stuff. What I see people doing a lot is actually just doing, if they're like tidyverse people, they do all their tidyverse data munging code. And then once their data is like in the format that they want to do machine learning, then they use this function called as H2O. They say as.h2o and your data frame, and then that will convert it to the H2O frame. So you can either do the data manipulation on the H2O frames themselves, or you can, so one thing that I'll say is you can't use an H2O frame and just do a whole bunch of tidyverse stuff on it. That's not supported. So either people leave it as a normal data frame, do all this like data munging, whatever, and then when it's ready to do the machine learning, convert it, or, you know, that's probably the most common. Or if you're a data table person, you do it all in data table and then convert it. And then the algorithms, there's a list here of what we've got. So these are the supervised ones. It's kind of a list of like things that you would recognize. So if you remember, like, we are implementing all of this stuff from scratch in a way that's distributed and scalable. So we only implement things that can be sort of scaled to bigger data, and then also like that people want. And if our customers ask us to add something, then we add it. So you will notice that this is a smaller list than what you could get in Tidy Models or Carrot, because I think, I don't know, Carrot has like 200 different options or something like that. So that's something to note. There's some unsupervised things that are useful. Isolation forest is good for anomaly detection, if that's something you like. PCA and this thing called GLRM, which you probably haven't heard of, but it's very similar to PCA, but it also works with categorical data. Yeah, clustering. There's some other sort of miscellaneous sort of, well, the bottom two, TF-IDF and Word2Vec, are both text converters. So if you have text, you can apply these algorithms and then convert it into numeric data, which then can be used in any of the algorithms. And then there's lots of other stuff here, but here's the AutoML page. And this is where you're going to find the code that you want to use if you want to do AutoML. I think we're going to reorganize this page soon, I think, to put the code at the top. So it might look different the next time you look at it, but there's a Python tab too, but we've got R here, and here's just, you know, a very simple example. Here's your data. So if you would like to try this on your own data, you can follow this example if you have a CSV file, or if you have it in a data frame, you can use the as.h2o function to convert it to that. So I would say train, then you have like the arrow, and then as.h2o, and then parens, and then the name of your data frame or your tibble or whatever it is. So, and then, here's one thing that I didn't mention, but so I should mention it. So if you have like, let's say you're doing binary classification, but your response column is encoded as numbers. So let's say it's like 0 and 1. One thing that we also do in H2O, because we're trying to be a very efficient library, is we pay special attention to like how the data is encoded. And so, and try to make it efficient. So if you want it to do classification, you actually have to tell it to be a factor. So that's what this extra step here is. In this particular data set, you had zeros and ones, so it didn't know if that was numeric or what that was. It's going to assume it's numeric until you tell it otherwise. If you have yes or no, that's obvious that it's going to be a factor. So when you import the data, it will already be a factor and it will do classification. But your response, the way that you tell an H2O algorithm, because we have the same function name for if you want to do regression or classification, the way that you tell it is by making the response column a factor column. Then it will do classification. And if it's numeric, it will do regression. So that's another thing that I see people getting confused about sometimes, because in R, there's lots of different ways. Some function, or some like machine learning functions will have a flag, like classification equals true. Some of them will have two different functions, one for classification, one for regression. There's different ways that you can tell it what you want it to do, but in H2O, this is the way that we do that. So, and then this is just showing how to do the AutoML. And you can do predict on, if you just pass it the AML object, it will predict on the leader model or the top model based on the leaderboard. You can also pass along like a single model here. There's like a pointer to the leader model that's just there for convenience. So either one of these works. And then I mentioned before, there's other stuff in the leaderboard that we can add if you want to add different columns to it, like prediction speed. Let's see. Okay, so there's, where do I have? Okay, yeah. So explainability, I say, AutoML objects are fully supported through explainability interface. Let me check on the time. Okay, I should be done in a minute. So this is the model explainability page. And so I mentioned the H2O.explain and explain row functions. So that's the main way that you can use it, and that will generate all the plots that you saw. But then each one of those plots also has its own function. So let's say, okay, so here's sort of a list of the different ones. So if you just want to do a residual analysis plot and you don't want everything else, there's a function that will just do the residual analysis plot. But basically H2O explain is just a wrapper that will call all of these different functions in a certain way. So here you can see the same images that I had before, and this just demonstrates how to do it like with a single function call. So variant plot, variant heat map, etc. So this is where you want to go to, number one, read a little bit more about what these things are, and then, be able to use them. So I think that, I'm going to stop sharing again and then reshare my slides, but then we can kind of just have a discussion and answer questions. I'll just point you, there's a few resources, like if you want to read about the H2O AutoML algorithm and how it works and everything else about it, I finally got around to writing a paper after 3 years. and it was published this summer at the ICML AutoML workshop. So that's a link to the paper. And one of the things it includes is a comparison to other AutoML frameworks. They're all in Python, so I'm not sure if that's a huge interest to this crowd, but I am part of another sort of consortium of AutoML researchers that produces this benchmarking framework for AutoML tools, and we're going to do a new updated version of all the tools, and there's going to be at least, well, there'll be one new R tool in there. That it's called MLR3 AutoML. That'll be like the only other one that kind of is out there to use if you want to look at it. But we haven't run the benchmark yet, so I don't know what it performs like. And then these are just some links. And again, I'll give you these slides, so don't feel like you have to like write everything down or whatnot. I should have given them to you before, but I did not. And I will leave it there, and then we can maybe just have questions. I think we have about, maybe 15 minutes or 20 minutes for questions. I probably talk too much, but.
No, that was fantastic. Thank you so much, Erin. I think I personally learned so much, and we had a very, very active chat. I don't know if you've seen it.
Okay, no, oh yeah, wow, there's a lot. I wasn't able to click on it and do it.
That's perfectly fine. So I think we can go through a couple of them. So let me just lead you through them. And to everyone else who's still having questions, please feel free to continue typing them in. If we don't have time to finish all of them, I think what we can do is maybe just to respond to the questions afterwards through an email, just to summarize all the points. So feel free to just continue. So I think there are a couple of questions. So one of them is from
saving them all.
Yeah, okay, perfect. So Michaela, for instance, asked whether there's a performance difference in R versus Python. Can you tell us any?
I think that's too hard of a question to answer, actually, because it all depends. I don't think generally there's a big difference between R and Python, but it's all depending on how you use it. And a lot of Python and R libraries use C++ code underneath. So yeah, I mean, there's a big difference between performance with C++ and Java and R and Python, but I would say R and Python are much more in the same category. And it really, really depends on like how you use it and the implementations that you're doing and the tricks that you know how to do as well.
Okay, perfect. Thanks. I hope that answered your question, Michaela. We also have one from Kelly. She's asking whether there's an optimal data size for optimal working of AutoML, or whether there's a guide to use size of train test ratio.
Okay. I would say there's like, if you have, use all the data that you have if you can. And like, I would say, it depends on the size of your machine and lots of things. So I think that, well, we have kind of like a rule of thumb in H2O, which is like, you want to have at least the amount of memory, like 4 times the amount of RAM as the size of your data set on disk. So if you have like a 1 gigabyte training set file on disk, you want to have at least 4 gigabytes in the H2O cluster. And the H2O cluster can be as big as the RAM on your machine. So that, but it is restricted by what you give the H2O cluster. So that's why I'm referring to that instead. So yeah, but if you're using AutoML and you like so that would be maybe like for training one model. But if you want to train like a lot of them, it's really hard to estimate actually. So I think you basically just try to do it, and if it doesn't work, like you need to get more RAM or something. Basically, it's kind of like a trial and error. That's probably another problem that could be solved by machine learning if you just gather enough data about like executing runs and what the resources are. You can kind of predict or whatnot. But
Yeah.
It's something that we're trying to kind of figure out a little bit better, because there's lots of things that we want to like be able to automatically parallelize in AutoML, but it's sort of a mystery of like, should we do like, 10 jobs at the same time? Should we do 5? Should we do 20? Like, it depends on the size of the data set, depends on how much resources you have on your machine. It's like a hard problem to kind of wrap your head around with like a simple solution. So yeah, I would say like, I mean, I can tell you, like, if you look at the H2O paper, I did like a scalability study. And so like I'm training data sets of size from like 10,000 rows all the way up to 100 million rows. And then you can like, I mean, I used a machine that has, I forget, actually, I used a whole bunch of different machines, but, I can pretty reasonably like train a lot of things on my laptop with H2O, because it's very efficient about its memory use. So maybe if you weren't able to train like your data set using a different library on your laptop, you could try H2O and see if it would be better. It probably would be, I think. So for most of, I mean, there's some packages out there that are also quite good, but that's one of the things that H2O does really well. And yeah. And then in terms of like the train test split, I don't know if there's like a real answer to that either. I mean, I would say that also depends on how much data you have. Like if you have a smaller amount of data, like you might want to save more of it for training, but then, maybe your estimates of what the performances is not as good. So then maybe you want to do cross-validation just to get a better, robust estimate of what your error is. But yeah, like I think more data is always better, but then it leads to other issues.
True. Just because you've just mentioned it, and I think this question also taps a little bit on what you've just mentioned regarding cross-validation. So, I'm probably going to pronounce the name wrong. Roshio is asking, could we use AutoML with cross-validation using predefined groups for k-fold? So is that possible?
Yeah, you can. So there's, by default, it will just randomly create the folds, but there's an argument called fold column. And if you set fold column equals to like the name of some column in your data set, and in that column, if you just have basically like the ID for whatever fold. So let's say you have 5 folds, and each row would have a number like between 1 and 5, assigning that row to that particular fold ID. So the way that you would provide that information to H2O is just having it in a column like that. And then you just say fold column equals whatever the name of that column is, and then it will use your custom folds.
Okay, cool, thanks. We still have a lot of questions. Let's just continue with this one. I think you very briefly mentioned it, but maybe just to clarify, there's a question on whether the data frame can be used, or that whether the method can be used with like a remote data frame such as Spark DF, or is it necessary for the data to be local before using H2O?
Okay, so you can, so there's a Spark package called sparkling water, which is the way that you use H2O with Spark. So that's, first of all, just to be aware, that's how you use it. And what actually happens with sparkling water is that if you have Spark data frames, it does actually copy them into H2O. And so you will basically be working with a copy of your data rather than your original data wherever it lives. There might be kind of another question in there as well, which is like, if your data is living like on the cloud somewhere in some cluster, like how do you do that? Like you can run H2O on your laptop, and when you do h2o.init, you can start an H2O cluster on some remote machine. Like let's say you have an Amazon AWS instance running, and that's where your Spark stuff is or your data is. You can connect to that remote cluster. I don't know if that's really another question that was sort of laced in there, but yeah, there's support for it, but you will actually be using a copy of the data.
Okay, perfect. Thanks, Erin. Yeah, I'm really much aware of time now. I also have a question myself that I'd like to ask you. I think AutoML is something that has a lot of potential, especially also helping content experts, for instance, to also try out first things by themselves. Do you personally see any risks of the use of AutoML by like people that might not be very familiar with how to do this?
Yeah, I do think there are a lot of risks. I don't think there's risks like to the person doing it, but I think, one of the things that can happen is that people don't really understand, like, let's say they're doing some machine learning and the rows represent people of some sort, and maybe there's different demographics of people, and maybe some groups are underrepresented in the data, and maybe just underrepresented like in the world, but also in the data. Like if you're not understanding how the machine learning is working on those particular subgroups, that can be quite harmful, because machine learning algorithms will just try to optimize like overall accuracy. And so sometimes that means like you don't care about this one group, because if there's so few examples, you're just going to be wrong all of the time. And we see that like there's this whole field around this like algorithmic bias and AI ethics and all of this stuff. And there's a lot of discussion going on in that world right now. If you Google around about that or go on Twitter in the past 2 weeks. So yeah, I think like another thing could be what's called data leakage, where you accidentally have some predictor columns that somehow encode the thing that you're trying to predict. And if you're not sort of aware of this concept or looking for that, you could think that you have a really good model that's predicting things really well, but then it's actually using data that like wouldn't be there like in a real scenario, or there's some other issue that you're like not seeing. So it's more like around the edges of like how the data is used, like things around the data I think are important. So I don't think you're going to get into any trouble with like training, like AutoML tools do make it easier for people that don't know about machine learning to do machine learning, but hopefully there's other people in the pipeline somewhere that do know enough to like double check your work. But I see also like more expert data scientists just using it as a way to like speed up their work. So there's a huge variety of like use cases, I think. But if you want to learn more about like potential harms of AutoML and automation, there's, I was gonna tell you to go to this link to my USAR keynote in July, where that was what I talked about. I talked about the whole thing. So that's something to check out. There's a video and there's slides, and I'll go into like lots of detail about algorithmic bias and what are the harms of machine learning or automating everything, and what can we do to prevent that and not, ruin the world.
Okay, thanks for the very brief overview, Erin. I have one last question. Maybe we can just finish this, because I think that taps into this quite a bit, also in terms of like having all kinds of people working in the machine learning pipeline, which I think has a lot of potential. And there's one question asking, in which ways does the AutoML help with reproducibility? Is it because you don't have to tune the models manually? Do you have like a log or anything that is kind of captured while you do that?
Yeah, so both things. So it's just, it's hard to like mess it up because there's not that many like parameters. So sometimes with reproducibility, like you might train models and you've set all these settings, and then somehow you might not document that properly. You thought it was a 5, but it was actually a 10, or, for some value or something like that. So in terms of like reproducibility, I think one, it's just easier to like, I guess it's not more reproducible than if you just were to run like a default random forest and that was it. But like if you do a whole big search and like all of this stuff, all this tuning and things like that, that can be harder to create like a reproducible version of. Sometimes people manually tweak things or just keep trying different settings. And so there's maybe not so much of a, when you're doing it that way, like documentation of all the things you tried and like how you arrived at the model that you got. So there's not really like a, yeah, like a audit history of everything, unless you have it all in your script, in which case then it is reproducible. But generally people try a lot of different experiments and then they end up at like the one where they encoded the variables like this, and then they did this and this, and then that's the script that you see, not all the things that they tried on the side. So with AutoML, you would know exactly everything that was evaluated, and there is a log of everything that happens, and that's stored like in the AutoML object as well. And so you know exactly everything that happened, and it's just all kind of bundled into the object for you. So that, in that sense, yeah, I think it's a little bit more reproducible.
Yeah, that sounds really good. Okay, perfect. Thank you so much, Erin. I wish I could give you a huge applause, but I guess you'll just hear mine for now. So thank you so much. I personally learned so much, and I'm also pretty sure that everyone within the audience learned a lot. I just heard something really loud. Okay. So yeah, I just want to thank you again so much for preparing the new slides for us and also giving us an introduction to this. I'm sure there are a lot more questions. We're going to try to answer to them. And if we need any of your help, we're going to just message you as well. And yeah, to everyone else, I hope you did enjoy the workshop. And if you have any feedback for us, please do let us know in the chat. Also, if you want to get in touch with Erin, you can always get in touch with her through Twitter, in case you haven't seen yet. And yeah, I guess that's like a good roundup for the year. So thanks everyone again for being part of this. And yeah, I guess that's a Merry Christmas and Happy New Year. And let's hope 2021 will be better than this. All right. Thank you so much, everyone. And yeah, have a good one.
Okay, thanks a lot. It was nice to be here.
Thank you so much, Erin. Bye.